To me, it is remarkable that this astonishing discovery the vastness and the emptiness of space has not attracted the imaginative attention of poets and religious thinkers. People are happy to contemplate the limitless power of God, a doubtful proposition at best, but quite unwilling to meditate creatively on the size of this extraordinary universe in which, through no virtue of their own, they find themselves. Naively, on one hand, they might have thought that poets and priests would be so utterly astonished by these scientific revelations that they would be working with a white-hot fury to try to embody them in the foundation of our culture. The psalmist who said, "When I consider thy heavens, the work of thy fingers, the moon and the stars, which thou hast ordained, what is man, that thou art mindful of him?" Was at least trying, within the limitations of his belief, to express his wonder at the universe visible to the naked eye, and the pettiness of man by comparison. And yet, his universe was a small, almost cozy affair compared to the one modern science had revealed to us. It is almost as if the utter insignificance of the Earth and the thin film of its biosphere has totally paralyzed the imagination, as if it were too dreadful to contemplate and therefore best ignored. I shall not discuss here how these very large distances are estimated. The distance of the main objects in the solar system can now be obtained very accurately by a combination of the theory of the solar mechanics and radar ranging. The distances of the nearest stars, by the way of their relative positions, change slightly when viewed from the different positions of the Earth in its yearly orbit around the Sun. After that, the arguments are more technical, less precise, but that the distances are the sort of size astronomers estimate, there is not the slightest doubt. I shall not discuss here how these very large distances are estimated. So far, we have been considering very large magnitudes. Fortunately, when we turn to very small distances and times, things are not quite so bad. We need to know the size of atoms. The size and contents of the tiny nucleus within each atom will concern us less compared to everyday things. This we can manage in two relatively small hops. Let us start with a millimeter. This distance, about a 25th of an inch, is easy for us to see with the naked eye. 1,000th part microns long. The wavelength of visible light which limits what we can see in a high-powered light microscope, is about half a micron long. We now go down by another factor of 1,000 to reach a length known as a nanometer. The typical distance between adjacent atoms bonded strongly together in an organic compound lies between a tenth and a fifth of this. Under the best conditions, we can see distances of a nanometer, or a little less, using an electron microscope, provided the specimen can be suitably prepared. Moreover, it is possible to exhibit pictures of a whole series of natural objects at every scale between a small group of atoms and a fleet. So that with a little practice, we can feel one scale merging into another. By contrast with the emptiness of space, the living world is crammed with detail at every level. The ease with which we can go from one scale to another should not blind us to the fact that the numbers of objects within a volume can be uncomfortably large. For example, a drop of water contains rather more than 1,000 billion water molecules. The short time we shall be concerned with will rarely be less than a picosecond. That is, 1/1,000,000th of a millionth of a second, though very much shorter times occur in nuclear reactions and in studies of subatomic particles. This minute interval is the short sort of time scale on which molecules are vibrating. But looked another way, it does not seem so outlandish. Consider the velocity of sound. In air, this is relatively slow, a little faster than most jet planes, being about 1,000 feet per second. If a flash of lightning is only a mile away, it will take a full 5 seconds for its sound to reach us. This velocity is, incidentally, approximately same as the average speed of molecules of gas in the air. In between their collisions with each other, the speed of sound in most solids is usually a little faster. Now we ask, how long will it take a second wave to pass over a small molecule? A simple calculation shows this to be in the picosecond range. This is just what one would expect, since this is about the same time scale on which the atoms of the molecule are vibrating against one another. What is important is that this is, roughly speaking, the pulse rate underlying chemical reactions. An enzyme, an organic catalyst, can react 1,000 or more times a second. This may appear fast to us, but this rate is really rather slow on the time scale of atomic vibration. Unfortunately, it is not so easy to convey the timescales in between a second and a picosecond, though a physical chemist can learn to feel at home over this fairly large range. Fortunately, we shall not be concerned directly with these very short times, though we shall see their effects indirectly. Most chemical reactions are really very rare events. The molecules usually move around intermittently and barge against one another many times before a rare lucky encounter allows them to hit each other strongly enough and in the correct direction to surmount their protective barriers and produce a chemical reaction. It is only because there are usually so many molecules when it's small volume, all doing this at the same time, that the rate of a chemical reaction appears to proceed quite smoothly. The chance variations are smoothed out by the large numbers involved. When we stand back and review once again these very different scales, the minute size of an atom and the almost unimaginable size of the universe, the pulse rate of chemical reaction compared to the deserts of vast eternity since the Big Bang. We see that in all these instances, our intuitions, based on our experience of everyday life, are likely to be highly misleading. By themselves, large numbers mean very little to us. That there is only one way to overcome this handicap, so natural to our human condition. We must calculate and recalculate, even though only approximately, to check and recheck our initial impressions until slowly, with time and constant application, the real world of the immensely small and the immensely great, becomes as familiar to us as the simple cradle of our common earthly experience.